Okay, so today we are going to continue with geometric proofs, and we'll put our focus on two-column proofs. And today we will do proofs that involve lines and angles. So properties about lines and angles, 7.1.3. All right, so our learning goal. So far, you've proven many properties of quadrilaterals, and now we want to turn our attention to proving important properties of lines and angles. And this visual is just to like sort of point you in the direction of what we're looking at, like what is the relationship between um, angles with parallel lines cut by a transversal, corresponding angles, alternate interior angles, the relationship between the three angles in a triangle, how many degrees all the way around a circle or partially around a circle, or the degrees of two angles that form a line and things like that. So this is just to like, give you visual reminders of some of the ideas that we have learned about lines and angles in the past. And today we're going to be proving several of these properties. Okay, so our essential questions really point us at the structure of a two-column proof more than like what properties are we proving today, just because we already know the properties we're going to prove today. We've already worked with them before in our math classes. We're just going to prove that they're always true. So what we want to do is be looking more at what is the structure of a two-column proof? What information is always at the beginning of the proof? What do the rest of the how do the rest of the statements relate to each other? And what must be included with every statement. And I just want you to like think about the proofs that we've been going through over the last couple of classes, and see if you have any clarity on any part of this set of essential questions. Just take a moment and reflect on that, what you know so far. So some people have responded with definitely like ideas that are right on. So the structure of a two-column proof is like, it's like a list with two columns, and the column on the left represents the statements or things we know to be true. The column on the right represents the reasons why we know they're true. So the information that's always at the beginning of a proof is the given information. Like, what do we have that we start with? What is our given? And then we go from there. The rest of the statements relate to each other in ways like they sort of create a chain like a chain between the initial like given statement and the conclusion, like the last statement, what we're trying to prove. So they connect the dots. It's sort of like a chain reaction. One statement leads to another statement, leads to another statement, leads to another statement. So then in the end, we can prove what we want to show about the conjecture. Every statement must have a reason. And the statements must follow from each other. Like we can't just like out of nowhere, do something that doesn't relate at all. Like these all need to relate to each other to build up to our conclusion. So that's just like a sort of broad insight into a two-column proof. And remember, a proof is sort of an organized argument for why something is always true. All right, so this is a definition that we just want to look back on and make sure that we are clear about before we go into our first proof today. So a perpendicular bisector, remember we constructed these. So a line is a perpendicular bisector of a segment if the line is perpendicular, that means at right angle, to the segment and passes through the midpoint, which means it divides the segment into two equal parts. So an additional bit of notation we could add to this diagram is like this equal to this. So this dashed line here is the perpendicular bisector of segment AB. It is at a right angle to the segment and it slices the segment in half. And the construction of this was like to create a circle where the center was A and the radius was the length of the segment. That's the first circle. And then create a matching circle with center B. And then the 2 points where the circles intersect end up guiding us with our perpendicular bisector to be able to slice that segment in half. So knowing this is just an important sort of pre-information for the proof we're going to do next. So basically, we look at this perpendicular bisector and we think, well, what might always be true besides the fact that it's a right angle, besides the fact that these segments would be equal, what else might be true about this perpendicular bisector and how it relates to the line segment? And that leads us to our next slide and this conjecture. The conjecture is points on a perpendicular bisector of a line segment are equidistant from the segment's endpoints. So what that means, just to clarify what that is even saying, is it's saying that no matter where we put this point P, it could be way out here, it could be here, it could be here, it could be the midpoint here, it could be down here. No matter where we put that point, the distance from the point to an end point, to A or to B, that these distances would be the same as each other. That's sort of the reasoning behind this conjecture. So those would be the same. Similarly, like if we put it from this point, those would be the same. It doesn't matter where we put it. The idea is that any point on the perpendicular bisector would be equal distance from point A and point B. So this is the idea that if we slide this point up and down the line, we're always going to be equal distance from point A to point B, no matter where we land. And so that's where the conjecture comes in. So what we're saying is all the points on a perpendicular bisector of a line segment are equidistant from the segment's endpoints. Equidistant means equal distance. And that's what we're going to prove. So I know I made it look kind of busy here, but I wanted to like demo the kind of concept behind this, okay? All right, so we're going to complete a 2-column proof, and we're going to show that P is the same distance from point A as it is from point B, no matter where P is. Where we want to show that this equals this. All right, so let's do it. Okay, so we pare down our given statement and what we're trying to prove to be more concise here. So our given statement is that PM, line PM, is the perpendicular bisector of segment AB, and that point M lies on AB. So this is all given. The diagram is given, the statement here is given. So we're going to go ahead and notice in our proof, the very first thing, PM is a perpendicular bisector of AB, that is given. So we can just go ahead and mark that as given. That's the reason we know this is true. And what's going to be important for us in order to prove that the segment PA is congruent to segment PB is to actually have those segments drawn into our diagram. So I'm going to get my line tool here, and I'm going to go ahead and actually connect the dots from point P to point A and from point P to point B. I don't have proof that they're equal yet. It's what we want to prove. But what's helpful about drawing those in is that that gives us a path forward for how to prove that, because once we draw in those auxiliary lines, those like extra lines to the diagram, you can see that we formed 2 triangles. So the reasoning now is going to follow like this. If we know that we have a perpendicular bisector, that tells us some things about the lengths that we have in like AM and BM. It tells us about the angle that the line and the segment intersect at. And then when we put in these lines, we have 2 triangles, which means if we can prove that triangles are congruent, then that would follow that any parts we hadn't discussed yet that are corresponding would also be congruent. So that's where our argument is going to lead. So what we need to do now is collect as much information about these 2 triangles they have in common as possible. So the first the next statement in our proof uses a reason of definition of perpendicular. So let's think about what information from the diagram we can draw, like we can pull from the idea that the line PM is perpendicular to the segment AB. So we know it's a right angle, and right angles are 90. So if we can say that that angle at point M is 90 degrees and this angle is also 90 degrees, then what we have between the two triangles is an angle in common. So this brings us to writing out our first, like our next statement. So we're going to say that the measure, so I'm going to use a little m for this, okay? The notation is interesting. Well, I'll try to clarify. So the measure of angle AMP will be equal to the measure of angle BMP, because they're both equal to 90 degrees. And they're both equal to 90 degrees. Okay, so if we know that they're perpendicular lines, the line and the segment are perpendicular, that means that the two angles that are formed here have to both be 90 degrees by the definition of perpendicular. So now we've established an angle in common between the two triangles. That's one part in common. We need one of those combos like side or angle side angle or something like that. So now let's collect some more information in common. So the next step, let me pause for a second. So our next statement now is something that we can draw from this reason, definition of a bisector. So remember in our given up here, that PM is a perpendicular bisector of AB. It's a bisector. And a bisector slices something in half. So if PM bisects AB, what that tells us is that segment AM is the same length as segment BM. And that's going to be our next statement. So our next statement is all about establishing that segment AM is the same length as segment BM. Okay, I'll add my notation on there. Oops. Okay, so segment AM is the same length as segment BM. And I'm going to add my little congruence squiggle. There we go. All right, by the definition of a bisector, because the line PM cuts it in half. Okay, so now let's collect what we have. We know we have an angle in common. We know we have a side length in common between the two sides. We just need one more thing. And so we look for anything else that these two triangles might have in common that we can actually know for sure. And what we can see is that they actually are side by side. They're sharing this segment from P to M. That piece of that side of both triangles is equal because it's on both triangles. So it's equal to itself. So the next thing we're going to be able to say is that segment PM is equal to segment PM. And I'll add my notation again. And if you recall the property that says that something is equal to itself, anytime something's equal to itself, we are using the reflexive property. The reflexive property tells us that we can state that something's equal to itself. And now check this out. What we have is, based on our list of things, we have an angle in common. We have a side in common. We have another side in common. And look at the order on our diagram. Side, then angle, then side. So we have two congruent triangles by side, angle, side congruence. Now we just need to name them. So we have triangle. Let's call it AMP on the left. And that's going to be congruent to triangle BMP on the right. So let me just add the rest of my notation here. So this is a congruent symbol. All right, so now we know we have congruent triangles. And once we know that, we can talk about any of the parts we haven't discussed yet. So we could determine that we had congruent angles at point A and point B. We could determine we have congruent angles up at point P, those two angles up there, or we could determine that side AP and side BP are the same lengths, which is totally what we were trying to prove. So this is our conclusion. PA is congruent to PB. And don't forget, when you finish a proof, you state it. So you're like, all right, check, we did it, or put a box or whatever, or you can write QED. And that shows that we are done. Okay, this next slide is kind of an informational slide. So just to clarify, what do we mean by conjecture and what do we mean by theorem? So there's basically a definition here. A conjecture is a statement or idea which is unproven, but it's thought to be true. The theorem is a mathematical statement that has been proven to be true. So we've been proving conjectures, and once we prove them, they become theorems. And pretty much everything we've proved is already a theorem or a property that's just like known as true. But we're learning how to do proofs. So there are plenty of conjectures out there that haven't been proved yet. They're just usually at a kind of different level of mathematics. So the following theorem has been proven many times using transformations on parallel lines. So we can use it to prove other useful properties. So this is a property, this is a theorem, the corresponding angles theorem, that says that when we have parallel lines that are cut by a transversal, the corresponding angles are congruent. So what we mean by corresponding angles is like angle 1 is corresponding to angle 5, so they would be congruent. Angle 2 is corresponding to angle 6, so they would be congruent, and so on. So we're not going to write a proof for corresponding angles theorem today. We're going to use it to prove something else. So we're assuming it's true, and that will help us as a tool to prove some other properties. All right, so here are more proofs about properties of lines and angles, and we're going to prove the following conjectures. Conjecture 1, that vertical angles are congruent. So remember what vertical angles look like when you have two lines that intersect. Oops, let's make that pink. When you have two lines that intersect, then the angles that result from those are vertical angles. So like this and this, those are vertical angles that would be congruent. Conjecture 2, when parallel lines are cut by a transversal, alternate interior angles are congruent. So just a reminder what that looks like. If we have parallel lines cut by a transversal, then alternate interior angles would be like this angle and this angle. They are on alternate sides of the transversal, but they're inside the parallel lines. And the third conjecture here is the measures of the interior angles of a triangle have a sum of 180 degrees. So if we had any random sized triangle The idea is that if I label these A, B, and C, is that basically A plus B plus C would equal 180. So this is what we want to prove. And so these three properties or theorems are the goal. Okay. All right, so proof of the vertical angles theorem. So what we're going to do is start with a diagram of two lines that cross and create angles. And then we're going to name angle 1 and angle 3 as vertical angles as our given. We're going to call them vertical angles. And then by the end, we're going to prove that they equal each other, that they're congruent to each other. So we start with our given and we end with what we're trying to prove. Okay, so looking at the structure of this proof, of course, we always want to start with what we're given. So we are given this diagram with angle 1 and angle 3 that are vertical angles. We establish what vertical angles are or look like using this. And that is given. And now we work our way through the argument. So step 2 says that angle 1 and angle 2 are supplementary. So let's look. Angle 1 and angle 2 are supplementary. That's true because linear pairs, they share that line. They span the line together. So if you add them up, they would make a line together. Linear pairs of angles like that are supplementary. So that's our reason why we know that. So now we're going to look for a different pair of supplementary angles because the next line also says linear pairs of angles are supplementary. So we know 1 and 2 are supplementary angles. We can also conclude that 2 and 3 are supplementary because they're a linear pair on the other line. So that's what our next statement will clarify. So we're going to write that angle 2 and angle 3 are supplementary because they are a linear pair as well. Now, look at statement 4. Statement 4 says that the measure of angle 1 plus the measure of angle 2 is 180 because that's the definition of supplementary. So what this is doing here is it's sort of connecting line 2 to line 4. You can see how if we know they're supplementary, then we know they add to 180 by the definition of supplementary. That's what supplementary means. So in a similar way, we're going to make the same statement about angle 2 and angle 3 that follows here. So angle 2 and angle 3 will add up to 180 as well. So the measure of angle 2 plus the measure of angle 3 equals 180 as well by the same reasoning. Okay, now we get to the sort of like, let's put it all together thing. So if we know that angle 1 plus angle 2 is 180 and angle 2 plus angle 3 is 180, then technically those two sort of combos of angles are equivalent. Like 1 plus 2 is equal to the same thing as 2 plus 3. So what we can do is basically substitute angle 2 plus angle 3 for the 180 in the previous step. And what we end up with is this statement that angle 1 plus angle 2 is equal to angle 2 plus angle 3 because we know they both equal 180. They equal the same thing, so they equal 180. So to do that, we could use some reasoning where we could say this is like equal values method, which we've done with substitution before. We could say this is substitution. I see somebody's thinking about transitive property that would also theoretically hold. So I'm going to use the substitution. All right. Now, for line 7, what we have to think about is, remember, every step leads to a future step somehow. So what we want to think about now is, how did step 6 get manipulated to give us step 7? What happened to step 6 that resulted in step 7? And you can see, let's look for the differences. So in step 6, we have an angle, the measure of angle 1. In step 7, we have the measure of angle 1. In step 6, we have the measure of angle 3 over on the right, and we have the measure of angle 3 in step 7. What's missing is this and this. Well, those are equivalent to each other. So technically what happened is angle 2 was subtracted on both sides. We just subtracted the two angles, the angles 2's. So we're allowed to do that in an equation. This is just an algebra step. When we subtract the same value from each side of an equation, the equations are still equivalent. They're still equal. So this is subtraction. I'm going to say subtraction property of equality, just to be all thorough. All right, and now we know the measure of angle 3 is equal to the measure of angle 1, 1 and 3, which means they must be congruent, because the definition of congruence is that two figures are congruent if their measures are equal. So there it is, QED. All right, now in this proof, we are going to prove alternate interior angles theorem. So I'm going to walk you through sort of the reasoning for this process, and then this is going to help us to be more formal in our proof. So I'm going to describe sort of how the argument is going to go. So we start with parallel lines. You can see how the given says that this is parallel to this. So this is parallel to this. And then we're trying to prove that angle 3 is equal to angle 5, these alternate interior angles. So what we're going to do in this argument is that we're going to establish a different pair of congruent angles. So we have our parallel lines. Notice on line 2 how it says right here, how it says angle 1 is congruent to angle 5. So if we can establish that angle 1 is equal to angle 5, if we can establish that, then we just need a connecting thing. So like, I want to show that angle 3 is equal to angle 5. Well, look at the relationship between angle 1 and angle 3. So what we're going to do is we're going to be like, well, angle 1 is equal to angle 3, and angle 3 and angle 1 is equal to angle 5. So then wouldn't these have to be equal to each other? That's sort of where our argument goes. So let's be formal about it. So let's start with our given thing. We have line M is parallel to line N. That's given. And I'm going to also add in from the diagram, just for real clarity, with transversal T. So I'm going to establish that my line M is parallel to line N, and I have a transversal T. And what that does is it means that we all know now that we have a transversal, and we have a ton of angles that are created by that. And that is what we are given. So our given is often like the thing that's written here, and also anything that is sort of shown in the diagram that would be a helpful structural tool for our proof. Now we know in step 2, in statement 2, that angle 1 is congruent to angle 5. And the reason we know that is because way back when we were talking about the definition of a theorem, we clarified that we had corresponding angles are congruent. We had corresponding angles are congruent as a theorem that we could use to prove other things. So since 1 and 5 are corresponding, We know corresponding angles are congruent. We can say that. All right, now the next step is to connect angle 1 with angle 3. So to connect angle 1 with angle 3, we have to look at that relationship. How does angle 1 and angle 3 relate? And those two are congruent as well because they are vertical angles. So now we're going to write that angle 1 is congruent to angle 3 because they're vertical angles. That's a congruence squiggle. Get the top of my congruence symbol. All right, now, so we know angle 1 equals angle 5. We know angle 1 equals angle 3. Now think back to what we're trying to prove. We're trying to prove that angle 3 equals angle 5. And that definitely follows from there. So now we can say that angle 3 is congruent to angle 5. And I'll point out like a clarification on that. So can you see how, since 1 equals 5 and 1 equals 3, then this 5 and this 3 would have to be equal to each other because they both are equal to 1. That's where the substitution comes in. So basically what happened is the 3 was substituted in for the 1. And now we have our final statement here. QED. Boom. So like if the same argument could help us prove other angle pairs are congruent as well. Like if I know angle 1 equals angle 5 and I know 5 equals angle 7, then 1 would have to equal 7 as well. Those are alternate exterior angles. So there's definitely like, we could have tried to prove that angle 4 equals angle 6 instead. Like there's lots of ways that we could build a similar argument to prove a different property. Okay, this is our last proof of today. And this one is to prove that the angles in a triangle add up to 180. So let's think about sort of how our argument is structured here. We want to show that angle 1 plus angle 2 plus angle 3 add up to 180. That's what we're trying to prove. So this is like what we're going for here, right? That the 3 angles inside the triangle are 180. We don't know that yet, but what we do know is, do you see how we have a line up here, AD, that's parallel to CB down here? And we have some transversals as well. AC is a transversal and AB is a transversal. So if we have parallel lines cut by a transversal, what happens is we end up with a bunch of useful angle pairs. And we just proved alternate interior angles. So I could show that this equals this at some point. I could also show that this equals this at some point because those are alternate interior angle pairs. And then there's something really special about these 3 angles together. So we're trying to prove that 1 plus 2 plus 3 add up to 180. What if we could start by saying 4 plus 5 plus 3 equals 180? And then connect the 4 and the 1 and connect the 5 and the 2. That would give us a path forward on this proof. So let's start with our given statement. Okay, so we have line AD is parallel to line segment CB. And I'm going to add in with transversals AC and AB. I think it's clearer. Oops, darn it. Oh my gosh, that's so annoying. I'm going to have to write that again. Okay, here we go. AD is parallel to CB with transversals AC and AB. Okay, and I'm going to add in some notation here. So these are all segments. So I'm just, oops, that's actually a line. This is a segment. This is a segment. This is a segment. This is a line. Okay. And this all is given information. So we're allowed to write that any kind of visual that helps us from the diagram is given, as well as anything listed as a given. Okay. Now, our first like technical statement of things that we know to be true about the angles that are formed. Angle 4 plus angle 3 plus angle 5 is 180. So let's look at those on our diagram. So what they're saying is angle 4 plus angle 3, oops, plus angle 5 is 180. And the reason this is true is because they actually form this line together. So you can see how, like, if I added them together, they would make a straight line. And we actually know that a straight line has a angle measure of 180. So what we're going to do is sort of explain that in our reason. So we're going to explain that a straight, a straight line has is a 180 degree, and the three angles form a line. So something like this clarifies that if we have three angles that form a straight line and we know straight lines make 180, then we're good. Okay, so now that we've established that 4 plus 3 plus 5 make 180, now let's connect up the other angles in the triangle. We need a way to connect to angle 1 and angle 2. So look in line 3, it says angle 4 and angle 1 are congruent. So angle 4 and angle 1 are congruent angles. We also know that angle 5 and angle 2 are congruent to each other. And the property that tells us this is the one we just proved on the previous slide, is that alternate interior angles are congruent. Oops. Alternate interior angles are congruent. We just proved that. That's a theorem. Okay, so here's the final connect. So if we know, sorry, and then line 4 says that means that the measure of angle 4 is congruent to the measure of angle 1, and the measure of angle 5 is congruent to the measure of angle 2 by the definition of congruence. So if we know we have congruent angles, then we know that their measures are equal. And this helps us to connect back to our equation. So now you can see how if we have the measure of angle 4 and the measure of angle 1 are equivalent, I can replace the measure of angle 4 in line 2 with an angle 1. And if we know the measure of angle 5 and angle 2 are congruent, then I can replace this with an angle 2. And look at what we're trying to prove, that 1 plus 2 plus 3 is 180. And if we substitute those numbers in, those angles in, then we'll have 1 plus 3 plus 2 is 180, which is basically the same statement in a different order. So now we've got it. The measure of angle 1 plus the measure of angle 3 plus the measure of angle 2 is equal to 180 degrees. you can add these terms in whatever order you want, but this line 5 is equivalent to what we're trying to prove. And we did this with a substitution. QED, and we have shown it.